Welcome back to the classroom. My name is Mr. Wong, and today we'll be covering a past paper question looking into Lenz's law and electromagnetism. So this is from the 2002 paper. This is question 23, and it's 7 marks in total. So let's get into answering it. So the very first one, it says, state Lenz's law. Lenz's law effectively states if you have an induced EMF, it will induce a current that produces a magnetic field to oppose the original change that made the induced EMF. So there's a couple of stages to that, so I'll write that down. So the induced EMF induces a current that also induces a magnetic field, whose force will oppose the original change in flux. Okay, so that's Lenz's laws there. And let's have a look at question B. So this is, I guess, a nice example of showing how Lenz's law works. You have a metal rod and it's being pushed upwards here. It's experiencing a change in flux as we pull the rod up away from the magnetic field lines, and so that gives us a nice little detail of the EMF being induced and so on. Okay, when the metal rod is moved upwards through the magnetic field as shown in the diagram, an EMF is induced between the two ends. Which end of the rod is negative? Okay, so to speak, we have a field line that goes through the rod like so, and the question is, as we bring the rod up, which direction is negative? So what I want you to try and picture is, using your right hand palm rule, we're going to try and work out the direction of the induced current. So here we show that it's going north to south, so your finger's pointing towards the right, your palm is pushing upwards. So you can see your thumb is pointing towards the end of X. Now, what's actually happening is, according to Lenz's law, we want to oppose this force pushing up. So we actually need to flip our hand around where our fingers are still pointing in the same direction. Our palm is pointing down, our right palm that is, and our right thumb is actually pointing towards the this end Y here. Okay, so if our conventional current, because that's what our thumb is, so our conventional current is saying the induced EMF is going in this particular direction here, that means that this side, the X side, is positive, the Y side is our negative end. So which end is negative? It's actually end Y, not X. Moving on, it says explain how the EMF is produced in the rod. This comes down to Faraday's law. So according to Faraday's law, as the rod moves upwards from the magnet, there is a change in the flux experienced by the conductor as a consequence EMF is induced in the conductor and it's described by our formula epsilon naught negative change in flux over the change in time. So as we said, the question is essentially asking us explain how the EMF was produced in the rod. We refer back to Faraday's law, that it's because of this rod moving upwards from the magnet that causes a change in flux for this rod, and as a consequence EMF is therefore induced. Okay, and what we could also say is the magnitude of the EMF induced would relate back to our equation here. So the magnitude of EMF induced would relate to the speed of motion of the rod and the change in flux. Okay, so off to the next question, and it says explain how the principle of induction can be used to heat a conductor. Okay, this one is an interesting one here. So if we induce EMF, that would create a current, and obviously as an electric current goes through a conductor, there is some kind of resistance. Okay, so if you recall what we talked about in module 4, it's actually due to as the charged particles, say in the case of electrons, are moving through a conductor, it's colliding with the ionic structure of the conductor, and during that collision, that transfer of energy is released as heat. So that's how we're going to explain it. So as the EMF will induce a electric or an electric current, these charged particles will collide with the how to put it, the ions, the metal ions of the conductor transforming the charge's kinetic energy into heat, thus causing the conductor to rise in temperature or to release heat. So causing the conductor to increase temperature as well. Okay, so that concludes our little summary section for this past paper question. So I did cover a few points. One was Faraday's law as well as Lenz's law, and then also what we can talk about with electromagnetic induction and heating in conductors. So I'll just zoom back to the questions that we have here. So we first talked about Lenz's law, then we looked at this little metal rod here. The main component, I guess, is this one that we show here. I want you to remember very closely, that is, what is Lenz's law, how do we apply it to find the induced EMF or induced current, and also how is EMF induced. That's because of Faraday's law, not Lenz's law. If you found this video useful, hit the like and subscribe button, and I'll see you next time.